This is lecture 13. I'm going to be talking about the central limit theorem and the law of large numbers. I'm not going to go over the formal theorem with you. I'm not going to present it in any kind of video format. I'm just going to refer you to the book, Linda Allen's book, to actually read it for yourself. My goal is to give you an intuitive idea of what the central limit theorem is. I don't want you to understand it word for word, verbatim, what the explicit terminology is. I want to give you an intuitive idea of what it's talking about. So in order to do that, we need to remember the normal distribution. So the normal distribution for a random variable, a continuous random variable, has PDF given by this, where here you have mean mu and variance sigma squared. Standard normal distribution, your mean's 0 and your variance is 1. So here is the picture of it. Basically, it's symmetric about your mean mu here. So in order to understand what a normal distribution is, maybe we need to understand what a normal distribution is not. So, or how far away from a normal distribution we are. So let's talk about skew. The terminology I want to introduce first is skew. Normal distribution has no skew, or basically skew equals 0. So it's symmetric about the mean as we saw in the previous slide. If you have a longer tail to the right, then it's said to be positively skewed. A longer tail to the left is said to be negatively skewed. So it looks like it's here it has the hump, but it has a little bit longer tail. Here it has our normal hump. I'm just going to call it a hump, and has our tail. And again, our mean is going to be somewhere around here, our mean here. But the biggest thing when we're talking about skew is where the tail is. Another terminology that helps us think about, how far away from normal we are is what's called kurtosis. So here, when we have a pointy, this is our standard one. This is our standard normal distribution. Sometimes we could have a pointier peak. This is called having a positive kurtosis. So you have a pointier peak and it's basically skinnier and pointier. Here, on the other hand, you could have smoother in the middle and it could have smaller tails. And this is called a negative kurtosis. So both of these are how much away from the normal distribution you have. So this is our normal distribution. And again, skew and kurtosis are indicators of how normal a distribution is or is not. Okay, so now the idea of the central limit theorem. We can start off with any distribution that has a well-defined mean and variance. So this is a distribution. It's not one that you would see in the books because it's not a normal distribution. And by normal, I don't mean normal distribution. It's not a standard distribution. That's probably the better word. So this isn't a standard distribution that you would see anywhere. So here you have that the mean is somewhere around 3.5. You have a small probability of getting 3 and 4, larger probability of getting 1 or 6. So now let's suppose I take n samples, and in my example I think I'm going to take 4 samples. Let's suppose I take n samples from the distribution, and then I calculate what the mean is. So what I'm going to do is I'm going to calculate the mean, and I'm going to do this several different times. So here I take a sample of 4 numbers. I do it once. I get the number 1, 1, 3, and 6. I look at what the mean is. I get 2.75. So here I'm going to plot the mean. And then I do this again. So I take, again, 4 samples. I get 3, 4, 3, and 1. I take the mean. I get 2.75 again. So here's my 2.75. I do this a third time. I take 4 numbers from my distribution here. I get 1, 1, 6, and 6. So calculate the mean, I get 3.5, and I plot it. So here's my 3.5. So notice there's no probability of getting a 2, no probability of getting a 5 here. So just be aware when you're looking at this, what the probabilities are, you're going to get something. So now I do this multiple times. So here I did it 3 times, and I just plotted it just to give you a feel for it. Let's say I do this 10,000 times. So I take 10,000 samples of size 4, I calculate the mean, and then I plot the mean. And what I could see is something that looks a little bit like this. This isn't exactly from this example, but I could see something that looks something like this, and it starts to look like a normal distribution. This distribution, so through this histogram, right, that I have, is called a sample distribution of sample mean. So I take a sample from some kind of distribution. In my previous one, here's what my distribution looks like. It has a well-defined mean and variance, but it looks a little odd. I take a sample. So I take a sample and I take the mean from it. So I'm taking the sample mean. That's what I call the sample mean. And I look at the frequencies of those sample mean. And that's what I'm plotting here. How often do I get this number? So in the previous example, how often did I get 2.75? How often do I get 3 point, whatever it was, 3.5? Okay, so you can go to this website. Let's see if it'll actually go here. Here we go. So I can go to this website, and you can read all of this if you want to. I'm just going to click begin. So here, I'm going to start off with let's say a skewed distribution. So here's a skewed distribution. And I'm going to look at an example of what we're actually doing. So if I draw a sample of 5, so this is exactly like what I was doing before. I take a sample of 5 numbers from my distribution and I plot the mean. I do this again. And I plot the mean. So I can do this multiple times. Plot the mean. So do this several times. Let's say I do this 5 times. Then here my sample size is 5, sorry. So my sample size is 5. Let's suppose I do a sample size of 10,000. And I plot this over and over again. Notice that my mean is close to the mean of my that I had for my population to begin with. If I do this 100,000 times, 100,000 samples for my distribution, then again my mean is really close to what it was previously. So I can create a custom distribution. So you can create anything that you want. So I create something odd here. So let's animate it again. Now here I took a sample of 5, I plot it. Take another sample of 5, plot it. So now let me clear that. So if I take a sample of 10,000, well, it's kind of looking like a normal. Here I can do fit normal. Let's do this 100,000 times. Let's clear this lower one. 100,000 times. Fit my normal. Well, let's suppose I do a sample size now of 10. And I do this 10,000 times. Well, that's looking a little closer to the normal, right? So let's suppose I take a sample of 16 and do this 100,000 times. So it's looking like a pretty good fit for my normal distribution. And let's suppose I do 25. I'm going to do this 100,000 times, and it's looking a lot like a normal distribution. So compare this to if I did n equals 2, 100,000 times. Does this look like a normal distribution? No. If I do n equals 5, 100,000 times, it looks more like a normal distribution. Still not quite there. Do n equals 10, 100,000 times. Oh, we're starting to get what looks like more like a normal distribution. 16, do it 100,000 times. Starting to get more like a normal distribution. 25, 100,000 times. So notice each time I each time I increase my sample size, it looks more like a normal distribution. So if I only picked 2 from my original sample, so I'm going to pick 2 numbers, and I'm going to run this 100,000 times. Well, I mean, it's going to look really similar to what my normal distribution is, right? So I'm picking 2 numbers from here, I'm averaging them together. It's going to look a lot like what this is. But now when I pick more numbers, so when I pick 5, and again, doing this at that 100,000 times, it starts to look a little bit more like a normal distribution because I'm averaging more numbers together, right? So, and then when I get to about 10, and I pick 10 numbers 100,000 times, then this is really starting to look like a normal distribution. So, my skew, my kurtosis, again, there's some skew and some kurtosis, so this tells us how far away from the normal distribution we are. Let's see if I do 25. Look at my skew is getting closer to 0, right? So what I want you to do is after you watch this video, I want you to go to this site and play with it for yourself. So I want you to look at what the skew and kurtosis is, depending upon here what number I use. And you can also do this, like, let's say if I take the median of a pick. Let's do this 100,000 times. So if I take the median and I only have 5 versus if I do 25, here, median doesn't quite work quite the same, but you see the general idea of here with the distribution of the means. This is really what we're talking about when we're talking about the central limit theorem. Okay, so going back here to our slide, ignore this thing. So in our original example, we took a sample size of 4. We found the sample mean. So what was the mean of that sample size of 4? Do we get a normal distribution if we do this 100,000 times? Probably not. If we think about taking a sample size of 1, then definitely not, right? So the mean is just going to be the one number that we get. So we're going to have basically the same distribution that we started with. N equals 2 is a little bit better, but you even saw in that animation that's not great. N equals 5, it kept getting better. By the time you got to about 10 or 20, it was typically good. It looks more like a normal distribution. The skew was small, the kurtosis was smaller. So the central limit theorem basically says that if the sample size is large enough and the mean of the sample is computed and it's done many times, so in our example we were doing 100,000 times on the animation, then the distribution of the sample means will approach a normal distribution. So that's basically the idea of the central limit theorem. Large sample, find the mean of the large sample, do it multiple times, and you're going to, regardless of what distribution you start off with, and it's going to approach a normal distribution. Okay, so this is the end of Module 2. You should be able to do the quiz and the assignments at the end of this section. And have fun, and always ask me questions if you